Okay, so this is 311. This covers the reciprocal functions. Okay, not inverse functions, not sine inverse, cosine inverse, tangent inverse, not those. These are reciprocal functions, meaning 1 over sine, 1 over cosine. Yeah, so he asked, can you have inverses of reciprocal functions? Yes, you can. Yes, you can. Hopefully we don't have that today. But yeah, it would be really easy to say secant inverse. So that's going to be 1 over cosine inverse, right? That gets real hairy. So it says, just when you thought these trigonometric functions couldn't get any more exciting, today we get to learn about 3 additional trig functions. The good news is that while these are 3 new functions, they correspond to the sine, cosine, and tangent functions we already know and love. And love at Roslyn. And love. So these new functions should not be too difficult for us to incorporate into our existing knowledge and quickly understand the ideas behind them. Okay, so secant. Secant's the first one here. Secant x is equal to 1 over cosine x, where cosine x is not 0. So what do you think the graph of secant looks like?
It's got all ones u's and upside down u's with asymptotes.
Where are the asymptotes?
Anywhere where cosine x is 0.
Anywhere where cosine x would be 0. Yeah, because secant's 1 over cosine. So if cosine equals 0, and I'm trying to divide by that, that's going to be undefined. Okay, so secant x has asymptotes every time cosine equals 0. If you'll remember, cosine x has asymptotes at pi over 2 plus pi k. We did this. So does secant x. Not cosine has asymptotes. Cosine is 0 at pi over 2. And 3 pi over 2. And if you kept going around, that would be again at 5 pi over 2. Okay? Are y'all following that? Cosecant is the reciprocal of sine, 1 over sine x. So cosecant is going to look pretty similar to secant, except that it's going to be undefined every time sine equals 0. So look at this sine curve. It's running right through here. Whoop, 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 whoop. And every time my sine curve hits the x-axis, cosecant is asymptotic. Can you see it? Every time sine hits the x-axis, cosecant has an asymptote. Cosecant is undefined. Okay. And the last one that we'll talk about is cotangent. Cotangent is 1 over tangent. If tangent is sine over cosine, cotangent is cosine over sine. So its asymptotes actually line up with cosecant because they both are undefined when sine equals 0. Did you hear me? What did I just say?
They're both undefined when sine equals 0.
What?
Cotangent
And?
cosecant.
Now we're talking. Okay, the rule of thumb on reciprocal function is this. No cos go together. Because I always try to figure out which ones pair up. No cos go together. So cosecant cannot go with cosine. Because they're both cos. Cosecant goes with sine. Secant goes with cosine. Cotangent goes with
Tangent.
okay? No cos go together. Does that make sense? No cos. So cosecant with sine, secant with cosine. Because it feels like if I was going to pair them up, I would say cosecant and cosine. But no cos go together. Okay? I don't know. Just no cos go together. The ranges. So the range on sine and cosine is -1 to +1. That oscillates right between those two y values, -1 and +1. Well, the reciprocal functions have reciprocal ranges. So it's actually undefined between -1 and 1. So it's everything but that. If you look at this spelled out down here at the bottom, it goes from -infinity to -1, and then picks up again and goes from 1 to infinity. So there's a gap in between that runs from -1 to +1. Okay? Y'all are looking at me like you're understanding, but I don't think it's going in.
What's the U?
There is no homework for this
You
lesson.
said that at the beginning, Lily.
Okay, example 1. Also at the top, you see the graph for cotangent. Okay. Example 1, it says, let f of x equal 3 secant of 2x. Which of the following is a vertical asymptote for the graph of f? Well, this is going to happen for secant every time cosine equals 0. You're following that? So when does cosine equal 0? Pi over 2?
And half of that because the 2 is
And so your period's pi and x equal.
So at pi over 2 plus 2 pi k, these are the intervals for where we would have cosine equal to 0. Cosine equals 0 at pi over 2 plus 2 pi k and at 3 pi over 2. Okay? We're going to set this argument 2x equal to that. Those are when our intervals of vertical asymptotes are going to occur. If we set this argument 2 pi or 2x equal to those vertical asymptotes and solve for x, we'll find the vertical asymptotes on this function. So how would I solve for x here? Divide by 2. So x is equal to pi over 4 plus pi k, right? But that part kind of gets thrown out here.
Sine is 0.
Are we understanding that? So you have to know where are your asymptotes on the parent function, and then you set your argument equal to that and solve.
For number 2, could you use 0 or would you have to use pi?
You have to use pi. Yeah. So the second one, cosecant of pi x, where are the vertical asymptotes? So those happen every time sine is 0. So where does sine equal 0? Every pi. So Truett asked, could I not use 0 there? No, because that's going to play really funny. We want to have a pi. So pi plus 2 pi k. And again, this part, it's not asking that. It just wants to know where is a vertical asymptote. So we'll set pi x equal to pi and solve for x. And what do we get? 1. That has an vertical asymptote at pi.
I was trying to find the period.
Well, the period's pi.
Yeah.
Actually, the period would be
2. Because if you do 2 pi over pi,
2 pi over pi would be 2.
weird. I was looking, I was like,
Example 3, it says let h of theta equal 3 cosecant of pi over 2. What gives the range? What gives the range? Okay, so which of these numbers up here is going to modify the range? The 3, the amplitude, right? So our range was supposed to be for cosecant, we're supposed to go negative infinity to 1. Sorry, negative infinity to negative 1 and 1 to infinity. But instead, that gets all multiplied by 3. So it's going to go from negative infinity, that's an infinity, by the way, negative infinity to negative 3 and 3 to infinity. Do you see how that amplitude is changing our range here?
how do we know it would be 1? Oh, because it says 3.
Because it's 3.
Because it shows the other stuff too.
Any questions on that one? Any other questions on that? So your amplitude is going to make it have a vertical stretch, which is going to change the range. Cool? Number 4, let k of x equal negative 5 cotangent of 2 pi x. Which of the following is a vertical asymptote on the graph of k? So let's talk vertical asymptotes. Again, that's going to happen when sine is 0. Because cotangent is cosine over sine. So every time sine equals 0, this function's supposed to have a vertical asymptote. When is that? When does sine equal 0? Pi. So we're going to set our argument 2 pi x equal to pi plus 2 pi k, right? We could do that. We want to solve for x. So we're going to divide both sides by 2 pi. And we can find our vertical asymptotes at x is equal to 1/2. My pi cancels.
Oh, yeah, you're so right.
X is equal to 1/2. How are we doing?
Good.
We're okay? You feel like you understand? Okay, so on the next page it says, just as we were able to solve equations involving sine, cosine, and tangent functions, we can similarly solve equations involving their reciprocals. To do this, it's generally best to isolate the trig function first. Isolate the trig function first. Once the trig function is isolated, we can use reciprocal properties to rewrite the equation in terms of sine, cosine, or tangent. This will allow us to use our previous knowledge. Okay. So here we go. It says let f of x equal 4 cosecant x plus 3 and g of x be 11. In the xy plane, what are the coordinates of the points of intersection of f and g? So what do we want? Good. We want f to equal g. So we write out 4 cosecant x plus 3 equal to 11. Everybody okay so far? Isolate the trig function first. So our first move is going to be subtract 3. Good. Subtract 3. So 4 cosecant x is equal to 8. Divide by the 4. Cosecant of x is 2. That's not super helpful, right? Except that if I flip both sides of this equation, and I can write it like 1 over cosecant x is equal to 1 over half, right? So I'm taking the 2 and the cosecant and I'm going like this. It was 2 over 1, now it's 1 over 2. It was cosecant x over 1, now it's 1 over cosecant. What is no cos go together. So 1 over cosecant is equal to sine. So sine x equals half. So x is sine inverse of 1/2, and we're on the interval from 0 to 2 pi. When is that? Positive 1/2. When x is pi over 6? 5 pi over 6. Wham bam. Okay, so you've got to know things. You've got to know that cosecant x is 1 over sine, and that goes both ways. So 1 over cosecant is sine. Okay, that's the move we just made. It works with secant. It works with cotangent. Cool?
Sine inverse is cosecant.
No. True. I'm going to yell. He just said sine inverse is cosecant. No, it's not. That's a lie. That was not Truett. That was Billy Bob. They're not inverses. We're not saying the inverse. Look, we said sine inverse. That gives me the angle, right, given a leg. These are reciprocals. Two different things. Billy Bob's on the right page now.
So, would that be whenever cosecant inverse would come into play? We just have
Well, we usually don't. I mean, if I can turn it into sine. Because up here the question would have been x equals cosecant inverse of 2. And cosecant inverse of 2 is the same as sine inverse of half. Way more better,
Sine inverse is.
right? I would rather transform it back into sine, cosine, and tangent than try to deal with cosecant inverse. Turn it into one of your reciprocal functions and invert those. Okay.
So,
What's your question?
no.
No. Billy Bob has no questions. All right, example 6. Let h of x equal 3 minus 1/2. I'm going to move, y'all. I'm